Hey everybody, welcome to another calculus video. Today we are dealing in section 4.6, which is called linearization. And I do this a little bit differently than your textbook. I will talk a little bit about how the textbook does it, but the truth is at the end of the day that linearization is simply using the tangent line, linear, to approximate your function. And so the idea behind it is this, is that if you have a tangent line and it is close to the point at which it's tangent, it's still close to your function. So as an example here, we have a function y equals x cubed minus 4x squared plus 3, and then the tangent line to that function at x equal 1. I've already figured this out earlier, and you could do it for practice, but it's the line y equals negative 5x plus 5. And so as you see, this blue line and this red line, they are very, very close, not just at the point 1, 0. That's the only time they actually touch physically. They only touch at one point. But you can see that the red and the blue are just totally right next to each other when it comes to much of this portion of the function. Now eventually the red function goes on to change direction and your line stays straight, but you can see that if you were to pick a number close to 1, say somewhere up here, point 0.5. Okay, 0.5 is 2.5 on the blue, but when you go to 0.5 on the red, you're at 2.125. So, but those are very, very close, right? And so you can see how the straight line could be used to approximate values of the red line. So that's what linear approximation is. That's what linearization is. And that's all we're doing. So how do we figure this out? If there's two questions that really could be asked for this section, all right? And one is to just find the linearization for a function. And if that's asked, well, that's just find the tangent line. That's all it is. Okay, whereas then the second thing we could do is use linearization to approximate. All right, and that's really where the big piece of this section comes in, because we just did, at least in my class, I know that the book has a whole chapter here between this, but we just did section 3.6, which is tangent lines and velocity. So now we've got linearization coming right after that, and hopefully you guys can see those dovetailing together. So let me just give you an example here. Use linearization to approximate the value of the square root of 10. Well, how in the world am I going to do that? What's my function? Well, my function then is square root of x, and what's the closest value to the square root of 10 that you actually know? We're going to use, we call it an a sometimes, a equal to 9. That's going to be my place where I take the derivative and I find the tangent line at x equal 9. Okay, so we're going to use what is often called a equal 9. And again, here's the thing. In the book, they give you this funky linearization formula. L of x equals f of a plus f prime of a x minus a. All right, well, that looks all confusing or whatever until you recognize that this is just a y. This is y1. This is your slope, and this is x minus x1. So this is just the point slope formula rewritten using some specific terminology for your function. So I'm not going to expect you to memorize this formula. If you want to memorize it, that's great. That's fine by me. But basically, when you say use linearization, when you see that there, and if I say use linearization, you're going to just find the tangent line. So how do I find the tangent line for this function? Well, I take the derivative. Remember, this is x to the 1/2. So we bring the 1/2 down, x to the negative 1/2. And then we find the slope by plugging in the value that we can use, the 9 in this case. So we get 1/2, 9 to the minus 1/2. Remember that square root of 9 is 3, negative puts it in the bottom, so you get 1 over 2 times 3, or 1 over 6. Okay. What's my point? That's my slope. What's my point? My point is 9 square root of 9, right? You plug a into f to get the point, and so my point is 9 comma 3. And so then I'm going to just do this point slope formula, y minus y1 equals 1/6 x minus x1, which is 9. And then if you solve for y, you get 1/6 x minus 9 over 6, which is 3/2, negative 3/2, and then you add 3 to that, you end up with a plus 3/2. Okay, so this is the tangent line to the curve y equals square root of x at the point x equal 9. Okay, so let me show you the picture just to make sure you're following. Okay, so here they are intersecting at the point 9, 3. The blue is the tangent line, the red is our actual curve of the square root of x, and so you can see clearly that those are going to be pretty good approximators. Okay, so then we're going to use the value for y equals 1/6 x plus 3/2 to approximate the square root of 10. Okay, so we just plug it in, right? We just take y equals 1/6 times 10 plus 3/2. So we'll do a little fraction work here, 10 over 6, and then 3/2 becomes 9 out of 6, and so we get 19 out of 6. Okay, 19 over 6. 19 over 6 is approximately 3.167 if you plug that into your calculator. And if you actually do the square root of 10 in your calculator, okay, if you actually plug that in, you get 3.162. Well, that's a pretty darn good approximation, right? Within 5 1/1000ths, that's a pretty darn good approximation. So that's how we do linear approximation. I have to either give you the A, or it has to be pretty obvious for you to do that, and then you just kind of do this process, all right? So let's have you do one, all right? And I'll give you the information, all right? So we want to approximate the value of e to the point 2. All right, so what's your function? Your function's e to the x. And what's the value that we know very well? A is equal to 0, because we know e to the 0 is 1, right? So we're going to use that. So here's your function. Here's the point at which you find the tangent line for that function. So take a few minutes, hit pause, go through the process. If you need to go back and look at the previous one as an example, go for it, and we'll work through it together. But go ahead and give this a shot. Find the tangent line first, and then approximate. Okay, so tangent line. First thing we need to do is find the derivative. Of course, the derivative of e to the x is e to the x. And so the slope is f prime at 0, which is e to the 0, which is 1. And the point we already found is 0, 1. Plug in 0, you get 1. So you get y minus y1 equals m times x minus x1. And so you get y equals x plus 1 as your tangent line. If you want to approximate e to the 0.2, we're going to plug in 0.2 for x. Right? We don't plug in e to the 0.2. We're looking for just, this is my x that I'm looking for. So I plug in 0.2, I get 1.2. And that's my approximation. If you plug this into your calculator, you'll find that e to the 0.2 is actually 1.221. So again, very nice approximation within a couple hundredths, very close. And there you go. So that's really it. Now, some of the problems, you're going to see some stuff like dy or dx versus delta y and delta x. Remember that delta means change, and so these are the exact changes. So this is like the y minus y1 or the x minus x1, that kind of thing, where these are approximate changes. Okay, remember dy over dx is another way to write the derivative. So those are approximate changes, and so when you're looking at those kind of notations, just understand what you're looking at. But I try to use this straight out stuff. I don't try to get too crazy with notation and all that kind of stuff for this section. Okay, so take a look at some problems for 4.6 and play around in my math lab, and let me know if you have any questions. Thanks.